Good morning and good afternoon. Thank you everyone for joining our March monthly webinar. This month we have a guest speaker, Dr. Gregory Sloop, who has actually given a webinar in the past with us. And he will also be talking today on the topic of blood viscosity. Just a quick bio on Dr. Sloop. Dr. Sloop is the Associate Professor of Pathology at Idaho College of Osteopathic Medicine, and also the author and editor of his book, Blood Viscosity, Its Role in Cardiovascular Pathophysiology and Hematology. It is 53 peer-reviewed, he has 53, peer-reviewed publications on PubMed, and he is a former chairman of pathology and laboratory director at Benefits Hospital in Great Falls, Montana, as well as the associate professor of pathology at the Louisiana State University School of Medicine in New Orleans. He enjoys living with 5 cats, 2 of whom are blind, and is a mad scientist in the kitchen, and also understands the importance of blood viscosity. Now, without further ado, I'd like to go ahead and introduce Dr. Sloop. Right before that, I did want to mention that this webinar will be recorded, and the recording will be sent to every single person who is attending and has also signed up for the webinar. So Dr. Sloop, I'll go ahead and give you the mic.
Thank you very much, Grace. If I was a highfalutin kind of a guy, I would have named my presentation, Blood Viscosity is More Than Hemoglobin, or Hemoglobin is More Than Just Oxygen Transportation. This is what William Shakespeare would have called it, in a gentle poke at physicians like myself who think of hemoglobin just in terms of its ability to deliver oxygen to the tissue and totally overlook its impact on blood viscosity. Every once in a while, I'll come across a physician that has a well-intentioned desire to improve his patient's condition, will actually over-transfuse that patient in the hope of improving oxygen transport in that patient, but doesn't understand that oxygen transportation is limited by blood viscosity. So the more you transfuse that patient, actually the less flow you're getting to that patient's tissue. And this situation is worsened in particular with banked red blood cells or erythrocytes, because erythrocytes become stiffer while they're stored in a blood bank. As you probably may be aware, erythrocytes have to deform in every time they pass through the circulation, because they have to traverse the smallest blood vessels, which are capillaries, and these have a diameter of 2 to 5 microns, and an erythrocyte has a diameter of 8 to 10 microns. So they have to deform to get through these very, very small blood vessels, and consequently, when they lose deformability, as they do when they're stored, they sort of clog up these blood vessels temporarily. They flow less well, and you're actually delivering less blood to that patient's tissue. And so it's very important for physicians to be aware of the impact of blood viscosity. Now, I'm going to take a little bit different view on blood than you're probably used to if you're a physician. I'm going to use the perspective called systems biology. It is a holistic approach. In fact, in the view that I'm going to look at the whole cardiovascular system, the heart and its impact on blood flow, and the impact of the blood vessels on blood flow. All these 3 things, the heart, the vessels, and the blood, all form a unified circulatory system. And I think to truly appreciate what's going on, you have to take that holistic view. That this contrasts to the reductionist view of hemoglobin and erythrocytes or red blood cells, is that they only transport oxygen, and that viewpoint totally overlooks the impact of blood viscosity and other cardiovascular phenomena such as wall shear stress, blood pressure, and systemic vascular resistance. We'll talk about all those phenomena throughout this presentation, but the reductionist viewpoint of hemoglobin just overlooks the impact of hemoglobin and red blood cells on all those other phenomena. So in this presentation, you'll see me borrow elements of engineering, material science, physics, and physical chemistry to try to explain blood viscosity. And a holistic approach is very, very important when you're talking about blood viscosity, because blood viscosity, I see it as an emergent phenomenon. And an emergent phenomenon is one that only truly develops in its fullest form when all the elements of a system are allowed to interact. In terms of blood viscosity, what this means is the viscosity is the ultimate result of the hematocrit, or the concentration of hemoglobin, the erythrocyte deformability, the amount of erythrocyte aggregations, which we'll talk about, the erythrocyte zeta potential, as well as the viscosity of plasma, which is additive to the viscosity imparted by the fraction of blood, which is composed of red blood cells. Plasma viscosity itself is affected by the concentration of every protein in the liquid part of blood, which is called the plasma. Not only the concentration, but the size of the proteins. Bigger proteins are going to impact blood viscosity and plasma viscosity more than smaller proteins, and also the shape of the protein. The more spherical a protein is, the less impact it has on plasma and blood viscosity. Some proteins are elongated and rod-shaped, and those proteins are going to have the largest impact on plasma viscosity and blood viscosity. The purpose of the cardiovascular system, of course, is to deliver every solute. We're talking about glucose as well as oxygen as efficiently as possible. You might think that, the faster the better, that you can deliver more oxygen with a very rapid, high velocity blood flow, but that's not really the case, because if blood flows too fast at too high of a velocity, turbulence can develop. And this is true not only for blood, but for every fluid. But turbulence is a particular problem with blood because the vortices in turbulent flow, the microvortices, can actually physically damage erythrocytes and cause them to release the hemoglobin, which goes out with the urine. And it can also plug up the tubules in the kidney and cause renal failure. So you want to avoid hemolysis, is what the phenomenon is called, and hemolysis can be caused by turbulent blood flow. You want to avoid that as much as possible. It is also a waste of energy. The energy generated by turbulence radiates out, is dissipated as sound. And so turbulent blood flow creates a sound which you can hear with a stethoscope. It causes heart murmurs, and in high output states such as pregnancy and anemia, when the heart has to work much harder, pump out much blood at a higher velocity, that creates this audible murmur, or a flow murmur. You can hear that with the stethoscope. And high velocity blood flow in blood vessels, the same phenomenon generates what's called a bruit, and that's audible turbulence overlying a blood vessel. And this particular figure, this is from Osborne Reynolds, the man who developed he quantified the flow phenomenon which result in turbulence. He quantified those in the 19th century. Reynolds number is the number that he used to quantify the likelihood of developing turbulence in flow. And as you can see from that equation, that the Reynolds number is positively associated with density, velocity, and the diameter of the tube it's flowed in. And at the bottom of that equation is dynamic viscosity. So the higher the blood viscosity, the lower the Reynolds number and the lower the tendency to develop turbulence. On the other hand, the higher the blood velocity, the higher the tendency to develop turbulence. And so those two have to be balanced. Viscosity adds work to the work of the heart. And so in its of itself, it also costs energy to pump highly viscous fluids. So you have to balance in your designing a cardiovascular system. You got to balance viscosity so that you don't use excess energy to push this blood around, and yet you have enough viscosity to prevent development of turbulence. Now, Reynolds number, you can occasionally see that in the medical literature, but I think a more important number in biology and cardiovascular physiology is actually the Dean number. And that's, I've done a PubMed search for Dean number and come up with maybe 6 hits. If you are familiar with PubMed, any search generates thousands of results typically, but the Dean number is not very often used in biomedical research. And I think it's much more important because blood vessels curve. That's necessary for anatomic reasons. For example, the surface of the heart is convex. And so blood vessels, arteries have to curve on top of the heart, the epicardial coronary arteries. The Dean number is important. As you can see from that equation, turbulence can develop at a much smaller Dean number than a Reynolds number. And so the criteria to maintain laminar flow in curved vessels is much more strict. A much lower Dean number is required to prevent the development of turbulence. And this is all because blood has momentum. It's a physical quantity like anything else. It has momentum, but this is not really widely appreciated in cardiovascular physiology. Blood velocity must be just right to prevent the development of turbulence and the waste of energy due to excess blood viscosity. Vascular curves have to be as gentle as possible, and of course that is anatomic constraints, and angles of branching must be as acute as possible. Those angles must be narrow. Obtuse angles will generate secondary blood flows, separation of blood flow, and create the hemodynamic milieu, which results in atherosclerosis. I'm not going to talk really much about atherosclerosis in this presentation, but it was a subject I talked about it at length in the last Reascense webinar. And so the point I'm trying to make is that vascular geometry is very important in determining blood flow and maximizing laminar flow. Now, a couple of terms I just want to get straight. Hemoglobin is the protein, of course, that carries oxygen in our bloodstream, and it's the protein with the highest concentration and the largest impact on blood flow. And it's carried within erythrocytes. And so I typically refer to the term hematocrit to quantitate the amount of hemoglobin in blood. Hematocrit is simply the percentage by volume of blood that is composed of erythrocytes. And you can see from that diagram, the normal hematocrit is going to be on the order of 40 to 45. It varies by sex. Females, the normal hematocrit is about 37%, 44, 45%. Males, it's going to be 39 to possibly 50%. The normal value for hematocrit is going to vary between laboratories and vary between populations. As you can see from this diagram, the contribution by volume of white blood cells and platelets, the other formed elements of blood, is vanishingly small. And oftentimes, if you spin blood down like this, you can't even see the layer of white blood cells and platelets, which is called the buffy coat. And of course, red blood cells are suspended in plasma, which is the liquid component of blood. And it's by far, volume-wise, generally the highest volume of blood. Now, blood is a colloid, or some might say blood is a colloidal suspension, and erythrocytes are the colloids. And this is important because, like any other colloid, blood is subject to spontaneous flocculation or agglutination. And what prevents that is the zeta potential of the erythrocytes. People that work in colloid chemistry understand that the higher the zeta potential, the less likely is a colloid to flocculate. And in flocculation, the particles agglutinate or flocculate and form a solid. And of course, you don't want that. So the higher the zeta potential, the less likely that is to happen. And if erythrocytes had no zeta potential, they would spontaneously agglutinate. Blood, the zeta potential in blood is calculated to be somewhere around -12 to -15 millivolts, which is quite small. The most stable colloidal suspensions have zeta potentials on the order of positive 60, an absolute value of 60 millivolts. Zeta potentials in the neighborhood of blood are classified as incipient unstable, meaning that they're just on the verge of agglutination or flocculation. That might seem like a design mistake until one considers that in two very important situations, inflammation and coagulation, blood has to essentially agglutinate, and focally, there are areas of hematocrit greater than 95%. So the erythrocytes have to be very closely packed in inflammation and coagulation. And that would take a lot of energy if erythrocytes had a higher zeta potential. So there is a benefit to having such a low zeta potential in erythrocytes. Now, this is a diagram to show you what the zeta potential is. The erythrocyte has a negative, electronegative surface charge because it's got sialic acid residues on its surface. And this negative surface charge is neutralized by cations, sodium ions in plasma, which themselves attract chloride anions. And so the interaction of the electronegativity and the ions in plasma create a cloud which surrounds every erythrocyte. And this cloud prevents the closer approach of two erythrocytes and is what prevents agglutination or flocculation of erythrocytes. So the zeta potential results from the interaction of the ionic strength of plasma and the surface charge of erythrocytes. Erythrocytes have a defined lifespan, probably on the order of about 70 days. And one of the things that contributes to their senescence or their aging is that they tend to lose the sialic acid on their surface. And I guess that's just physical trauma from, sequential deformation. And anyway, erythrocytes tend to have a lower zeta potential as they age before they are removed from the circulation by the spleen. Another very important situation where the zeta potential comes into play is in renal failure. And you've probably before heard of the microbiome, which are the bacteria that normally inhabit our gastrointestinal system. The microbiome has an impact on our well-being because these microbes, as part of their metabolism, they release organic acids into our bloodstream. These organic acids are usually monovalent, maybe bivalent, but much larger than the small ions, which typically compose the cloud surrounding the erythrocyte. So when these larger organic ions are incorporated into the erythrocyte cloud, they decrease the ionic strength of plasma, and they decrease the zeta potential and increase the likelihood of erythrocyte aggregation. And so that's one of the reasons why cardiovascular disease, atherosclerosis, is accelerated in renal failure patients. They have an increased concentration of these organic acids, the products of the microbiome, which are typically actively excreted by the kidney. And when that renal function is lost, the concentration of these ions increases in the bloodstream, reduces the erythrocyte zeta potential, increases erythrocyte aggregation, which increases low shear blood viscosity. And I'll get to that presently. This is a diagram from one of my publications, which shows the result of uric acid, which is an organic ion normally present in our bloodstream, the effect of elevated concentrations of uric acid on blood agglutination are what we typically call erythrocyte aggregation. Here you see these columns of erythrocytes, which people in laboratories, hospital laboratories call rouleaux, are stacks of coins. And this is simply because in this case, the zeta potential has been decreased because large uric acid anions are incorporated and displace smaller chloride ions in the plasma and decrease the size of the cloud surrounding an erythrocyte and allowing the closer approach of these erythrocytes. In this case, these erythrocytes were coated with a molecule, the immunoglobulin IgG. And this is a molecule that's moderate in size. Under ordinary circumstances, it cannot simultaneously bind to two erythrocytes and cause the development of these erythrocyte aggregations. But when the zeta potential is decreased, it becomes large enough to bind to two erythrocytes spontaneously and develop these erythrocyte aggregations, as you see here. There you can see an arrow in the upper left-hand corner, and that's pointing to an erythrocyte which has what's called echinocyte morphology. And this is an abnormality of erythrocyte shape. And as you might well guess from looking at that erythrocyte, it's not going to be as deformable as the typical erythrocyte, which has a biconcave shape. And you can see near the very middle of the photomicrograph, there's a biconcave erythrocyte. It looks like a target. There's a outer circular lighter color and a denser center. So that's the normal biconcave discocyte. And so these are erythrocyte aggregations which will increase blood viscosity at low shear rates. And this property, the combined properties of erythrocyte deformability, and erythrocyte aggregation make blood a non-Newtonian fluid. And that's a different behavior than what one sees in the typical fluids that we're familiar with, like gasoline or water. Those are non-Newtonian fluids, meaning that the viscosity is constant, no matter what the rate of shear or how fast that fluid flows. Blood will become more viscous the slower it flows because of the development of the erythrocyte aggregates, which we saw in the previous slide. At higher shear rates or higher velocities, normal erythrocytes will deform into what's called an ellipsoid. And they will also entrain, like imagine cyclists in a race, how the cyclists line up one behind the other. The lead cyclist is the one that's doing the hardest work, breaking apart the atmosphere, if you will, allowing the cyclists behind him to draft. That same behavior happens in red blood cells at high shear rates or high velocities. They entrain and allow the other red blood cells to draft, and that phenomenon decreases blood viscosity at high shear rates and high velocities. When blood flow slows down, as in veins, then there's a tendency for erythrocyte aggregation. And that occurs normally, but in certain conditions, there's an increased tendency towards erythrocyte aggregation, and that's called hyperaggregation. And that occurs when there's elevations of proteins associated with the inflammatory response. And the main one that is responsible for this is a protein called fibrinogen. It's a large protein and it has a rod-like structure. So it's not spherical at all. So it has a big impact on plasma viscosity, but it also has a very big impact on erythrocyte aggregation. This protein is large enough to normally bind to erythrocytes and develop and augment erythrocyte aggregation all by itself. And so inflammation increases blood viscosity. Inflammation is a hyperviscous state, and increases in blood viscosity have an adverse effect on blood flow, as you might imagine. Viscous oil is going to flow less well than water. And so when blood becomes more viscous, it has a threefold decrease in blood flow. So a change in blood viscosity has a threefold inverse effect on blood flow. So it doesn't take a whole lot of increased blood viscosity to have a notable serious impact on blood flow and decreased delivery of oxygen and all the other metabolic substrates necessary for life. Blood has a tendency to clot or form a thrombus if it doesn't flow at all. And so that's sluggish blood flow is just a manifestation of high blood viscosity. And so you're probably familiar with the phenomenon of deep venous thrombosis. If you sit on an airplane for too long, you're immobile, blood tends to collect in the veins of your leg and will spontaneously form a thrombus. And that can be a life-threatening situation if those thrombi dislodge and go to your lungs and block blood flow through your lungs. That's called a pulmonary thromboembolus, can be life-threatening. And that's simply a manifestation of increased blood viscosity. The third way that blood viscosity causes pathology or disease is it increases vascular resistance directly. And so increased blood viscosity can cause hypertension. It can elevate the blood pressure simply because it increases the resistance to flow of blood. I think the pandemic that we're just getting out of, the COVID-19 pandemic, taught physicians a lot about blood viscosity, because almost all of the complications which made the news during the pandemic were caused by elevated blood viscosity. And again, this was a manifestation of elevated concentrations of fibrinogen, and mainly fibrinogen. And this is a normal part of inflammation. However, the concentrations of the protein fibrinogen in COVID-19 patients were the highest that I've ever seen um, in laboratory medicine. And as a result of that, there was an increased incidence of thrombosis in young patients in intensive care units. And these patients were on prophylactic anticoagulation. Every patient that goes into an intensive care unit, because they're immobile, is at risk for developing sluggish blood flow in their lower extremities and getting pulmonary emboli. And for that reason, it's pretty much standard of practice to put patients on anticoagulants to prevent the development of these blood clots. Well, these patients with extremely viscous blood and COVID-19 developed these thrombi. And this made the news because it happened in young patients, patients that were otherwise not at risk for developing thrombosis. So that's one complication. That's actually the first complication I remember being reported early in the pandemic. The one that struck me the most was what was called in the news as silent hypoxemia or happy hypoxemia. That really gave me pause. These were patients that sort of presented to their physician or presented to their emergency room with no signs of respiratory distress. They did not complain of shortness of breath, but when physicians performed pulse oximetry or checked their oxygen saturations, they were unexpectedly very low. Some of you may be familiar with a pulse oximeter. They sell them at drugstores. Every patient in an intensive care unit has their oxygen saturations continuously monitored by a pulse oximeter. It looks like a clothespin that closes on one of your fingers, typically your index finger, and there's a little red light in it, and it detects wavelengths of hemoglobin. And the wavelength of the light emitted by the hemoglobin varies with its oxygenation status. And so these pulse oximeters assess the oxygen saturation of the hemoglobin. And so anyways, these patients with silent hypoxemia would present with oxygen saturations of 60, 70, 80, the normal being about 93 and above. And as I said before, without complaining of shortness of breath or anything. And this really gave the physicians pause. Again, these are patients that would present, their initial presentation was with silent hypoxemia, and they may have come to seek medical attention because they were feeling ill and subsequently found to have silent hypoxemia. And this was unexplained until finally people looked at the impact of increased blood viscosity on blood flow to the lungs. Of course, the lungs is where oxygen exchange occurs. Carbon dioxide is released from the bloodstream into the alveoli in the lung, and oxygen in the alveoli is taken up by the lung. If you've got decreased blood flow to the lungs, you're going to have decreased gas exchange. Your oxygen saturations will fall. Your carbon dioxide saturations will increase. And this is strictly a manifestation of increased blood viscosity and decreased blood flow to the lungs. Early in the pandemic, these patients would have been intubated and placed on mechanical ventilators. And that was found to not really help these patients that much. These mechanical ventilators put positive pressure into the lungs, and this positive pressure works against the blood pressure, causing blood to flow into the lungs, which is generally lower than the blood flow to everywhere else in the body. And so positive pressure ventilation with these mechanical ventilators decreased pulmonary blood flow, and by themselves would cause decreased oxygen concentrations in these patients. So it was eventually found out during the course of the pandemic that you shouldn't mechanically ventilate or intubate these patients, but just deliver oxygen at the highest feasible concentrations. And so that was one of the things that was learned in the COVID-19 pandemic. The phenomenon of myocarditis has gotten a lot of attention in the press, both as well, predominantly as a result of vaccination, but it does occur, and depending on the source you look at, it does occur more frequently in the course of COVID-19 than in the vaccination. That's a somewhat controversial topic, but I think it's probably true because the degree of inflammation in the infection is greater than the degree of inflammation caused by the vaccination. But the vaccine, given the vaccine immunization, does cause an inflammatory response. And the same inflammatory response caused by vaccination will increase your blood viscosity and decrease blood flow to the heart. And when that happens, there's a mismatch of oxygen demand and oxygen supply. And that causes cardiovascular damage, which is detected in the hospital laboratory as elevations of troponin T is the most common test. And when this protein, troponin T, is elevated in the bloodstream, it's a manifestation of myocarditis. And so that's the etiology, the cause of the myocarditis, which is seen following vaccination. And it typically strikes younger males. Males have more viscous blood as a baseline because of their higher blood viscosity. As I said earlier, males have a higher blood viscosity than females. And healthy young males will tend to have a more vigorous inflammatory response and a higher blood viscosity following vaccination. And so that's why that particular group is most prone to develop myocarditis following vaccination. But myocarditis does occur in the course of, as a complication of COVID-19 itself. The subject of long COVID is getting more attention now that the pandemic itself seems to be waning. And I believe myself and my colleagues believe that increased blood viscosity also plays a role in long COVID. As I said before, the erythrocytes have to deform into the capillaries to get through, to complete their circuit through the circulation. And when blood is more viscous, it tends to stay put in these capillaries. It's a state called stasis. Now, the endothelial cells, the cells which form the capillary, depend on oxygen from the blood within that they contain. And so if this blood becomes stagnant within these capillaries, the capillary itself can die due to decreased oxygenation. One of the manifestations under the microscope of long COVID is decreased capillary density or capillary rarefaction. There's a fewer number of capillaries in the tissue. And my colleagues and I think that this is what causes long COVID. So again, that's a manifestation of elevated blood viscosity, causes stasis of blood in the capillaries, decreased supply of oxygen to the capillary itself. The capillary itself dies and results in a prolonged, maybe even permanent decrease of blood flow to that tissue. Now, this slide is not meant to be read. It's just a resource for when this presentation is up on the YouTube that you can refer to and read the publications my group has put out on COVID-19. As you can see, we've published extensively on the effect of elevated blood viscosity and the complications of COVID-19. There's one paper here in particular I want to direct your attention to, and that's the second one, which discusses the oligonucleotide or the RNA fragment, PURUU. That's simply the sequence of nucleotides in the RNA that elicits an inflammatory response by what's called innate immunity. And this particular oligonucleotide is present in very, very high copy numbers in the coronavirus, which causes COVID-19. And the very high copy number of this oligonucleotide, PURUU, is what causes hyperinflammation and hyperviscosity in COVID-19 patients. But that same oligonucleotide is present in a fairly high copy number in respiratory syncytial virus, which I think we just finished an epidemic of that virus, and that can cause complications of hyperviscosity. One of the rare but pathologically interesting complications seen with, in particular, with respiratory syncytial virus caused by hyperviscosity is what's called neonatal apnea. Decreased perfusion of the respiratory centers causes a decreased respiratory drive in very young and oftentimes infants that are what are called ex-preemies. But these infants have a decreased respiratory drive naturally, and that respiratory drive is further dampened by the decreased blood flow caused by hyperviscosity and due to the PUR oligonucleotide in respiratory syncytial virus. There's also a fairly high copy number in Ebola viruses, and our group has written about that as well. Now, I've mentioned that blood viscosity increases the workload on the heart. And so in my daydreaming, I've often wondered what would happen. Shouldn't there be a health benefit to having low blood viscosity? In fact, I preach drinking 40 ounces of water a day, 5 8-ounce glasses of water a day, and that's been shown to prolong life in the Adventist Health Study. And I've also preach donating blood because that will lower your blood viscosity, and it's been shown to decrease your cardiovascular risk. My group has a paper that's in press right now, and hopefully that'll get published soon to make that case once again, although that case has been made time and time again, that blood viscosity is decreased by blood donation. So anyways, shouldn't lower blood viscosity be better? And of course, that's intuitively true. But what is the floor to blood viscosity? And received wisdom tells us that blood viscosity is just the cost of requiring hemoglobin to transport oxygen. That in a perfect world, we would have all hemoglobin without the blood viscosity, and that would decrease the burden, the workload on the heart. That's not possible in this world, but blood viscosity is generally perceived as a negative thing. And my latest investigations begun when a colleague provided me with this paper about the blood boosting capacity of this fish, Pagnathenia borchgravinki. It's an inhabitant of Antarctic waters, and it's got the amazing ability to change its blood viscosity in accordance with how much oxygen its body needs. And when it's at rest, and these fish are fortunate enough to spend a lot of time at rest, they feed maybe once a week, at least in captivity, they're fed once a week. And so they spend a lot of time digesting and spend a lot of time resting. And their hematocrit, their ability to deliver oxygen to the tissue, varies along with the workload on the heart in accordance with how much oxygen is required by that tissue. When these fish are forced to exercise, when they're prodded with a stick in the fish tank, their hematocrit is increased. And that goes along with increased cardiac output and increased physical activity, which you intuitively understand requires the delivery of more oxygen. So their hematocrit goes up. After they're fed, there's going to be increased blood flow to the gastrointestinal tract. So that counts too. So that's sort of an intermediate state. There's still some work going, the work of taking up the nutrients that they have been ingested. And so that's an intermediate state with an intermediate level of hematocrit. And after these fish are at rest and they're copacetic and they're not doing anything, their hematocrit is the lowest. And so this was a paper that a colleague gave to me a couple of years ago, which actually introduced me to the subject of ice fish, which has started me on my latest investigations. This is a picture of Canocephalus aceratus, which is an ice fish of the, I think it's a suborder Chanichthyeidae. These fish are the only vertebrates that lack hemoglobin. And that just blew my mind when I found out there were such organisms. And I was very anxious to delve into the literature and see what their blood viscosity was going to be, because I thought, well, this is an opportunity to test the fitness of extremely low blood viscosity, low burden on the heart. And lo and behold, the blood viscosity in this ice fish is nearly identical to the blood viscosity of humans. So that was an unexpected finding to me and caused me to ask the question, what is the floor to blood viscosity? What is the lowest blood viscosity that's compatible with life? And so that's what I've been investigating ever since that point. I think I've got an answer for you. But this is a diagram that I borrowed from a paper in which the factorial scope for cardiac output was measured in this fish, Pagnathenia borchgravinki. Factorial scope is simply the ratio of maximal to baseline, and there can be a factorial scope of many different physiologic parameters. In any case, in this paper, what was studied was the factorial scope, or the ratio of maximal cardiac output to baseline cardiac output. And again, these fish were subjected to exercise to assess their maximal cardiac output. And so in the conditions of this experiment, some fish were acclimated to -1 degrees, which is their basic physiologic temperature, and other fish were acclimated to 6 degrees centigrade, which is a little bit warmer. Now, what happens in acclimation is there is decreased blood viscosity because there's decreased concentrations of antifreeze glycoprotein. And that's a glycoprotein which is felt to be necessary for these fish to prevent the development of ice crystals in their bloodstream. And of course, these ice crystals would cause physical trauma in the microvasculature. And so that has to be prevented. And these fish have this molecule, antifreeze glycoprotein, AFGP, which prevents that from happening. It's also the molecule which is in the highest concentration in the blood of these fish. And so it is what determines blood viscosity in these ice fish. And so the viscosity is going to vary in these two populations of fish. And what it was found was that the factorial scope for cardiac output was greatest in acclimated fish, despite the decreased amount of oxygen. And that the result of this experiment told me that cardiac output has to be matched to blood viscosity. And the reason for that is if there's cardiac output which is too high for the blood viscosity, you're going to lose laminar flow, develop turbulence, waste energy, and that loss of energy is going to decrease the maximal cardiac output. And that's what this diagram is all about. And so one more experiment with a related fish, another ice fish, Trematomus bernacki, it's a relative of Pagnothenia porchgravinki. The investigators basically eliminated the ability of the hemoglobin in this fish to transport oxygen by carboxylating it. And what they found amazingly, when the ability of the hemoglobin in this fish is eliminated, the ability to transport oxygen, the fish does not miss a beat. In other words, viscosity and hemoglobin in this fish is there only to provide blood viscosity and not oxygen transportation. This fish in the cold, oxygen-rich water of Antarctica doesn't need hemoglobin. The solubility of oxygen increases with decreased temperature. And so these fish are able to survive simply from the oxygen dissolved in bodily fluids without transporting oxygen via hemoglobin. And that is truly an amazing finding. And so in these fish, hemoglobin is only there, or is only necessary for its viscogenic effect, its viscosity producing effect. In humans, it's estimated that the minimal hematocrit necessary for survival in the literature is 24%. I think it's probably a little bit lower than that. I've seen patients with hematocrits of 20, 21% that are surviving. They're not able to chop wood or scoop the snow from their driveway, but they're alive and they're making it. And so the hemoglobin above that which is necessary to transport oxygen is present in the humans just for its viscogenic activity. So the hemoglobin in humans is there in large part to provide viscosity and prevent the development of turbulence. And I'm going to go at length into this one paper. I'm starting to run long, so I'll hurry it up. But this paper came out in 1969, the mechanism by which plethora suppresses erythropoiesis. What these experimenters did, again, was poison the ability of the hemoglobin to transport oxygen, and then they put these mice in hypo oxygenated atmosphere, decreased atmosphere, decreased oxygen availability of oxygen. So ordinarily that would drive increased production of erythropoietin, which is the hormone which causes production of red blood cells. But when these mice, experimental mice, were hyperviscous, they didn't develop an erythropoietic increased erythropoiesis despite being in their hypoxic atmosphere. And what this tells you is that the body prioritizes blood viscosity over maximizing oxygen transport. And the reason for that is that blood has to deliver everything, not just oxygen. You can die almost as fast from running out of glucose as you can from running out of oxygen. So the blood has to deliver everything. And for that reason, the body optimizes blood viscosity over oxygen transport. When patients, humans get too anemic, they can develop a disease called high output heart failure. And that's characterized by a very loud murmur. The turbulence that I've talked about earlier develops because the cardiac output is so high, and it develops turbulence. This wastes energy. These patients have very greatly decreased capacity for exercise, all the other symptoms of heart failure, but their heart is working just fine. It's just that the viscosity of blood is too low. So my colleague George Pop was the first one who I ever heard say that blood viscosity has to be part of the internal milieu. That was a concept brought about, initiated by the father of physiology, Claude Bertrand, in France in the 19th century. And blood viscosity is so important, it has to be controlled. And there are two mechanisms by which blood viscosity is controlled. And the first is called the systemic vascular resistance response. And that is elicited by sensors in the left ventricle, the ventricle which pumps blood to the rest of the body. When there's increased systemic vascular resistance as caused by increased blood viscosity, this is sensed by mechanoreceptors in the ventricle, and that initiates a response that decreases the hematocrit. And on the other hand, you've got sensors in something called the carotid sinus. These are sensors on the inner lining of the carotid sinus, and it can sense wall shear rate. And when wall shear rate becomes too high, that's a sense to decrease blood viscosity. And it does that by decreasing the production of erythropoietin. And there's one thing in this diagram I want you to see is that because of the geometry of this dilatation in the carotid sinus, the Reynolds number is such that an area of flow recirculation develops. And that is what we call a pattern of preferential blood flow. And so the point on this is that blood viscosity has to be just right for blood flow to be just right. If blood viscosity is too high, as you can see on the right side, blood velocity is decreased. When blood viscosity is just right, the difference of velocity of these different streamlines, the length of the arrow is proportional to velocity of the streamline, is just right. If viscosity is too low, there's going to be a greater discrepancy in the velocity of these streamlines, and that's what leads to the development of vortices and turbulence. And these preferential flow patterns are an important part of physiology. In an anatomic structure called the carotid sinus, vortices typically develop with every heartbeat, and these help close the valve, which prevents blood from backflowing into the heart after it contracts in systole. My favorite example of preferential blood flow is in the frog heart, which only has 3 chambers. It's got 2 aorta and 1 ventricle. And in the human, it has a 4-chambered heart, and this allows complete separation of oxygenated and unoxygenated blood. The oxygenated blood goes to the rest of the body. The unoxygenated blood goes to the lungs, and those are kept completely separate. Well, the same thing happens in the frog heart because of preferential flow. You can see in this diagram, oxygenated blood is indicated by the red arrows, and the unoxygenated blood is in the black arrows. And so even though there is no formal anatomic separation, there is functional separation called preferential blood flows. And you can imagine if blood was way too viscous, these preferential blood flows would be lost. Blood would tend to back up in the atria before it got to the ventricle. But if blood was not viscous enough, you could see that these preferential blood flows would be lost as well. There would be development of vortices and mixing of blood in this single ventricle. The result of that would be blood with lower oxygen saturation would go to this is an amphibian heart, for example, a frog. Lower oxygen content would be transported to the frog. Muscles are not going to perform with develop the same power, and that's going to affect the physical performance on the frog. It's not going to be able to leap from one lily pad to the next. And because viscosity is just right, there's preferential blood flow and separation of oxygenated and deoxygenated blood in the frog heart, despite there not being a formal separation. So in conclusion, blood viscosity must be normal for normal blood flow to occur. Hemoglobin has both oxygen transporting and viscogenic activity. The control of blood viscosity is robust in humans. There's 2 mechanisms which look at 2 different aspects of blood viscosity: systemic vascular resistance and wall shear rate. And finally, blood viscosity is part of the internal milieu. Just want to say thanks to Grace and the team at Reascense. I want to thank Yelena Holtz, the librarian at Idaho College of Osteopathic Medicine. She gets me the papers that I need. And of course, I want to thank my esteemed collaborators. I'd be very pleased to answer any questions which you might have.
All right, Dr. Sloop, so we have a couple questions right now, so I'll go ahead and read the first one. Is the critical protein content, parentheses, amino acid, required for the blood viscosity for the balanced functioning of the body?
Yes. And so that's those amino acids, those proteins contribute to plasma viscosity, and that's part of the internal milieu and is controlled by the systemic vascular resistance. And the other axis is called the renin-angiotensin-aldosterone system. And so, yes, that is true.
Okay. Is there a way one can learn more about erythrocyte aggregation using dynamic oscillatory tests? specifically G prime and G double prime?
I'm afraid I don't know the answer to that. I'm not familiar with G prime or G double prime, but when the presentation's over, I'd be glad to discuss that with you. You can add a comment once the video is posted on the YouTube, and we can have a discourse on that. I'd be happy to learn about that. Thank you for the question.
All right. The third question is it not fibrinogen protein is the main culprit of blood viscosity variation?
Yes, that's true. Fibrinogen has a very big impact on blood viscosity because it is large enough to augment erythrocyte aggregation, and that increases the low shear viscosity. But at the same time, because it's a large asymmetric molecule, it increases plasma viscosity. And that's the reason why blood viscosity is so high in COVID-19.
Okay. Since blood is a non-Newtonian fluid, when we say blood viscosity, which viscosity would we be referring to? Is
Well,
it the zero shear viscosity?
okay, well, yeah, if you're performing an experiment, you have to define the conditions. And in writing, I generally specify whether I'm talking about low viscosity conditions, which I arbitrarily define as less than one inverse second, or high shear conditions, which I arbitrarily define as 100 inverse seconds being the unit of shear rate. And so you really have to define which shear domain you're talking about. And one of the deficiencies in the literature, because people don't really understand blood viscosity, it's not unusual to come across a paper where the shear conditions are not identified, and a value of blood viscosity is reported, but that's the value of that information is greatly limited if you don't know whether they're talking about high shear or low shear viscosity. The values of viscosity I talked about earlier in humans, 3.27 centipoise is the unit. That's that's high shear viscosity. Low shear viscosity is going to be on the order of 5. And so what is normal or abnormal strictly depends on what shear domain you're talking about.
Okay. Next question. Can you please comment if there are appreciable blood viscosity differences in high-level athletes?
That's a very interesting question. I don't think there is. One of the phenomena you can see in elite athletes is something called sports anemia. And that's what's called a dilutional anemia. The number of erythrocytes, the red cell mass, is the same. However, the amount of plasma is increased, and that causes a decrease in the measured hematocrit. But at the same time, it maintains blood viscosity. And so you might people that have this sports anemia, I've read that they're, upset by anemia, even though they're in great shape. But the fact of the matter is, this so-called sports anemia is a beneficial response because it decreases blood viscosity or allows blood viscosity to be maintained. These people have increased cardiac power as a result of training. That increases peak blood velocity and will increase wall shear rate at the carotid sinus, which I talked about. And so, because as a response to this increased wall shear rate, which results from increased cardiac power, the body responds by increasing plasma volume, which decreases the tendency or nullifies the increase shear rate, shear stress rather, in the carotid sinus. So I don't think that they do. Now, if you acutely increase your hematocrit by blood doping, illicit transfusion in an attempt to increase your athletic performance, that will increase blood viscosity. And as a matter of fact, before synthetic erythropoietin could be detected and athletes tested, a number of elite cyclists died from hyperviscosity as a result of blood doping. What would happen is their hematocrits would go up, which they could tolerate until they got some degree of dehydration during the race. Their blood viscosity went up and caused cardiac arrest. So that was a rambling answer. I hope I answered your question. That I guess the answer is in certain situations, blood viscosity is increased, but if there's no external influence, no blood doping, it's going to be the same.
Okay. I would love to get insights from you on the application of viscosity of blood as an indirect measure of hematocrit or fibrinogen concentration, and possibly using this information in clinical research.
Yeah, I think it has great application or great use for those applications. And so I'd be happy to help you if you contact me and point you in the right direction and how you might, perform that research. But I think that blood viscosity should be measured instead of lipid panels, for example. And I think it tells you more information about your risk of heart disease than the lipid profile. LDL, the bad cholesterol, increases your blood viscosity. HDL, your good cholesterol, decreases your blood viscosity. And so your blood viscosity tells you the same information, as well as the increased risk imparted by every other cardiovascular risk factor. And I did talk about that at greater length in the other webinar. So if you're interested, you might watch that other webinar. But I'd be pleased to try to help you out in any way I can. I think it's a perfect means of assessing hematocrit and fibrinogen.
All right. Are there any outward signs of decreased blood viscosity? Anything that a physician can use as a clue to warrant testing?
In decreased blood viscosity, yes, that systolic flow murmur that I talked about, it's not uncommon at all in anemic patients to hear this flow murmur. And the murmur is the result of increased cardiac output, which is a response to anemia and decreased ability of the blood to transport oxygen. And because of lower hemoglobin concentrations, lower hematocrit. And at the same time that there's a decreased ability of the blood to transport oxygen, there's decreased viscosity. And so the response to that increased cardiac output results in the development of turbulence. And so, yeah, low viscosity can be detected by a heart murmur.
Okay. If the RAA control system maintains viscosity, then you are saying that decreased hematocrit and or oxygen carrying ability can be attributed to other proteins effectively using up available viscosity. Is that correct? So essentially, anemia could actually be a second order effect of an inflammatory reaction.
Yes, And that anemia has a special name called the anemia of inflammation. And that's a not uncommon finding in hospitalized patients. Anemia of inflammation. It also goes by the name of anemia of chronic disease. And that is a result of the increased viscosity caused by generally immunoglobulins, and the body responds by decreasing the red cell mass to normalize blood viscosity. So in these patients with the anemia of chronic inflammation, their blood viscosity is normal, and the downside is this is achieved by reducing the hematocrit.
So when measuring whole blood viscosity, the lysis value goes down. Is that because the affected blood cells are greater than the cell height? Or how do we measure whole blood so that the lysis does not change?
I'm not sure what lysis means. Um, so I want to answer your question, but I'm a little bit I don't understand the terminology, and so maybe I'd ask you to write a comment once the video is posted on YouTube, and I can answer your question then. I'm sorry, I'm just not familiar with the terminology.
So Dr. Sloop, he just mentioned the red cells breaking down is equal to what lysis means, if that makes sense.
Yeah, well, that's hemolysis, but I forgot what the context of that is.
So
Is it
sorry, go ahead.
is it is the question, does hemolysis decrease your hematocrit? And to that, the answer is yes.
Mm-hmm. Yes, okay.
Okay.
How would you have any tips on measuring whole blood in that case?
Measuring whole blood viscosity?
Yes.
Is that what? Uh, well, I think Grace might be able to answer that question. There's several different methods of measuring blood viscosity, and I think Grace's method may be the best. So why don't you talk to Grace about that? She may have the instrument to help you out.
All right. And I'll be happy to send more information over after the question session. But we'll proceed with the next questions just to kind of keep it rolling. Let me see. Do you have any experience with endovascular simulators? If so, could you recommend any systems?
I'm not familiar with that. I'm sorry.
All right. So vein blood and artery blood viscosity is different. Does this difference change in disease, or does it often not change?
It changes in disease, and that's a very good question, and thank you for that. And what that question is recognizing is that arterial blood flow is high velocity and high shear, and so viscosity is going to be lower in that arterial blood flow. Venous blood flows slower and is more viscous, and so that's what is the important information imparted by that question. And I admit I forget the rest of the question. Can you repeat it, Grace?
Repeat the question.
Please, yeah.
Sure. So I'll just repeat from start to finish just so that you have everything.
Okay.
Vein blood and artery blood viscosity is different. Does this difference change in disease, or does the difference not change?
Okay, the difference does change in disease. In inflammation, low shear or venous blood viscosity increases to a greater extent than high shear blood viscosity. And that's because of the erythrocyte bridging caused by increased concentrations of fibrinogen. And so that causes really great increases in low shear blood viscosity, greatly decreasing perfusion of tissue and increasing the risk of thrombosis and those complications that we talked about in relation to COVID-19. So the answer is yes.
Perfect. And we have the last question. Do you think blood viscosity should be included in machine learning clinical prediction methods?
Yes, I think blood viscosity is of primary importance. As I mentioned, I think it's part of the internal milieu that Claude Bernard, uh, that concept that he came up with. And blood flow is not going to be normal if your blood viscosity is not right. And that's going to affect flow in your heart. Those vortices that I didn't mention, that figure was drawn by Leonardo da Vinci. He was the one that first realized that vortices develop. All of that goes out of whack if your blood viscosity is not right. So I do think that it's very important to measure blood viscosity. And I think that that's what my mission is, to try to increase awareness and measurement of blood viscosities in the clinical situation and also the research situation.
Okay. All right. So yeah, Dr. Sloop, we'll go ahead and conclude the webinar. Thank you so much for being the guest webinar speaker again for a second time. And for those of you who stayed and stuck through the whole question session, just a repeat reminder that we will prepare a recording of the webinar, and we will go ahead and send it out to everyone.
Thank you, Grace.
Thank you, Dr. Sloop.